All right, how's it going, everybody? We are here at the beginning of week 13. This week, we're going to discuss the chi-square distribution, and we're going to look at the series of tests that are associated with this guy. So far, the hypothesis tests that we performed this semester have all been about making decisions about a population parameter, either mu or p, our average or our population associated, or sorry, our average or proportion associated with a given population. And also, we looked at making decisions about the difference in averages or the difference in proportions between two populations. However, despite the fact that there's a bunch of different hypothesis tests that we've already looked at, all of them do the same thing in that all of them are responsible for helping us make decisions about where the center of a distribution is located. Our sampling distribution for the sample mean is centered at mu. Our sampling distribution for a sample proportion is centered at p. So these are representative of centers of distributions. In this chapter, we're instead going to look at hypothesis tests to make decisions about the shape and variance of distributions. Or when you see variance, you should think like standard deviation. Remember that every distribution has three shapes, or sorry, three features: a shape, a center, and a spread. So far, all the hypothesis tests that we've looked at so far are only for making decisions about the center of a distribution. We also want to talk about the other features of a distribution: its shape and its spread. And so in this chapter, we're going to see hypothesis tests for both of those types of features. We're going to say, does this distribution have the shape that I think it does? And does this distribution have the amount of variation that I think that it does? All right, we've already looked at average and proportion, our measures of center. So let's look at a whole bunch of different examples of questions that we can answer with these ideas that are associated with this chapter. So these are all questions that could be answered by the end of this chapter here. Is a certain coin a fair coin? And you should be asking yourself, how many times do you need to flip a coin for you to be convinced that it's a fair coin, a 50-50 coin? And that's kind of a weird question because even if I flipped a coin 10 times and got 9 heads and 1 tails, there's actually like a 2% chance that you're going to see a 9 and 1 split if you flip a coin 10 times. It's hard for, how many times do you really need to flip a coin for it to be fair, for you to be sure that it's fair, is kind of an interesting question. Is a certain die fair? If you rolled a die 50 times, could you confidently judge whether it's a fair die or whether maybe it's been loaded so that one of the sides is more likely to come up than another? How many times do you need to roll a die for you to be convinced that it's equally likely that you're going to see any given outcome? Do workers that work Monday through Friday from 9 to 5 take sick days evenly distributed throughout the week? It's often the suspicion of many employers that sick days are taken more often on Mondays and Fridays because they're not actually sick days, they're weekend extensions. And so an employer might want to perform a chi-squared test for goodness of fit to determine if his employees are in fact taking sick days uniformly across the week, which is what we would expect if they truly were sick days, or if they're perhaps more weighted towards Monday and Friday, which would be the case if they were not actually representative of sick days. Very similarly, next two questions: are women equally likely to give birth any day of the week? Are people equally likely to have heart attacks any day of the week? We would want to see what the distribution of births or of heart attacks are across each of the 7 days in a week and ask ourselves, does it seem like some sample of these has been drawn from a uniform distribution where there's an equal likelihood on each day of the week? Or is there maybe some reason why perhaps women are more likely to give birth on a certain day of the week, or that people are maybe more likely to have heart attacks on a given day of the week? Getting a little bit more technical here, a botanist perhaps is attempting to pollinate some plants, a desired cross pollination between two plants. If you've ever worked with plants, then you know that it can, in certain situations, be pretty difficult to guarantee a certain pollination because pollen's tiny and it gets everywhere. So maybe if a researcher is intending to cross two heterozygous plants, then they would expect to see different outcomes than if there was a plant with a heterozygous feature crossed with a homozygous dominant feature plant. And so what we're wondering here is, just based on looking at the features of the children plants, can we verify that the correct combination of parents was actually achieved in the pollination? Or can we perhaps determine that there was some unintended cross-pollination from a plant that did not have the desired phenotypes that we were looking to pollinate with right here? So this is a very good one for biology right here. We can look, without doing genetic testing, we can look at the proportions of the child plants and determine if we believe that the correct pollination had in fact occurred. And a couple more examples here. A poll is conducted of 100 men and 100 women from Eureka asking about their highest level of education. The researcher would like to know if a person's gender is independent of their education status. So this is an independence test. In this test right here, we're going to ask, are two variables independent of one another? Or does knowing the value of one variable help influence the values that we think that we'll see for the other variable? Here we're asking the question, is the variable education independent of the variable gender? Or does knowing somebody's gender status help us understand or help us predict what their education status is going to be? A similar question that we could ask with that same data set would be, do men and women's distributions of education status, are they the same, or is there a different distribution that men's education status follows than women's across the different groups of levels of education? So these are all types of questions that we'll be able to answer with the chi-square distribution that we're going to look at in chapter 11 here. So what's up with this chi-square distribution? So all the probabilities that we're going to compute this chapter will be from the chi-square distribution. You should notice that up until now, for all of our hypothesis testing that we've been doing, we have used only the standard normal distribution, the z distribution, or the student's t distribution. Every test statistic that you have computed in the last couple weeks has either been a z-score or a t-score. This week, we'll get a bunch of test statistics that are chi-squared values. I guess they're not typically called chi-squared scores, but they're still the test statistic. They're still a measure of deviation from the center of a distribution. They're still going to help us compute a p-value. We're still going to interpret our p-values in comparison to an alpha value, right? So a lot of things are going to stay the same. The one thing that's going to change is that we're going to compute our probabilities differently, using a different distribution than we've seen before, the chi-squared distribution. As with the t-distribution, this distribution's shape will depend on the number of degrees of freedom associated with the sample that we've taken. So just as we've needed to compute a number of degrees of freedom with the t-distribution, we will have to compute a number of degrees of freedom associated with the chi-square distribution. As we also saw with the t-distribution, some instances calculating the number of degrees of freedom is incredibly easy. We saw in some cases it was just n minus 1. In other cases, we saw that computing the degrees of freedom for a t-distribution was pretty complicated. We got that really gross formula last week. And so we'll see a similar thing here. Some of these will be slightly easier than others. Some of our degree of freedom information will be trivially easy. Others will require a little bit of calculation. We won't see one as bad as the gross one that we saw a few weeks ago, though. As with the t-distribution, right, again, still similar to the t-distribution, the chi-square distribution will also have the property that as our sample size gets larger and larger and larger, the shape of the chi-square distribution and the shape of the t-distribution both will become closer to being a normal distribution as our sample size gets larger and larger. And we'll be able to actually see a good graphical representation of that here in 1 minute. So here's a graph of some of the chi-square distributions here. They're graphing a chi-square distribution with different degrees of freedom that you can see over here, 2, 5, and 10 degrees of freedom. I know these colors are a little difficult to see here, so I want to point out to you where we have 2 degrees of freedom is this blue or purple decreasing line that's right here. And you should stop and take a moment and say the sentence to yourself in your head, this curve looks nothing like the other 2 curves. And that's true. The chi-square distribution changes quite a bit depending on how many degrees of freedom we're observing in our experiment here, which we'll get to their computation in a moment. So here we're seeing 2 degrees of freedom with this only decreasing curve. This red curve here is the chi-square distribution with 5 degrees of freedom. And the green curve is the chi-square distribution with 10 degrees of freedom. So a couple things again to notice here are this is not a symmetric distribution. You should notice that we do not have equal left and right sides. That's going to mean that we need to treat our left and right sides of this distribution independently. We can't do things like we've seen in the last couple of weeks where if we were looking at a two-tailed hypothesis test, to compute a p-value, we could compute just the area in one tail and multiply it by 2. We can't do that anymore because now the areas in the 2 tails are not going to be equal to each other here. Also notice that that in this graph, we're only graphing the positive, I should move my hand in the right direction, the positive chi-square values out here. Notice that this is only positive numbers. We don't have a side of the graph where there's negative x values, or I should say negative chi-square values out there. And algebraically, this makes a little bit of sense, even if we're not directly talking about what chi is. If we're squaring something to compute this number, squared numbers are always positive numbers. And we can see all these chi-square values sitting out here. They're all positive out there. And kind of remember, this is in contrast to the z distribution. The z distribution, we're centered at 0, and we can go one standard deviation above or one standard deviation below to a z value of -1. That's equally as common as a z value of +1. So the z distribution is split equally between +½ and -½ The chi-squared distribution only exists in the positive region of our graph. And I think I already said this. I added in this sentence right here, but I already said that up above. We'll need degrees of freedom for every single one of these computations that we're going to perform. And finally, before we see our first example, I kind of want to take a lap around this chapter here and show you what the upcoming 3 sections are associated with this chapter, since they're all very closely related. In section 11.2, which we're going to discuss today, is our goodness of fit test. In section 11.2, we're going to see things like this. Here's our example. We roll a die 60 times and we'd like to judge whether or not it's a fair die. The results of our rolls are given in this table. So here are our values 1 through 6 from the die. Here is the frequency that we observed that one value. Now I'm noticing right away that it seems like there's quite a lot of rolls of 6s out there, and all of the rest of them seem vaguely approximately uniformly distributed, right? But it does look to me like I got more 6s than I would expect to get. And I just say I'm saying that word expect all slowly and carefully, because expected number of rolls is something that's going to be very important to our calculation here today. In this scenario, we're comparing a sample of a single variable value to a hypothesized distribution. Notice that we kind of know what we expect to get. If we are going to roll a die 60 times and we are expecting that the outcomes are uniformly distributed, then I know that I expect to get, if there are 6 outcomes and 60 rolls of a die, then I expect to see each outcome 10 times. That would be my expected rolls of each frequency. And what we're going to do is we're going to compare our expected frequencies to our observed frequencies and see if the difference is large enough to convince us that this couldn't have come from a die that had a true uniform distribution of its values out there. So here our null and alternative hypotheses would be, in this case, the outcomes are uniformly distributed versus the outcomes are not uniformly distributed. In section 11.3, we're going to look at a test for independence, and we might ask, does gender influence education status? We might want to know, does knowing a person's gender help to inform us about what level of education they may have received? In this example, we will see hypotheses of the variables gender and education status are independent of one another. Or alternatively, we might see some evidence that suggests, for example, if I know that you're a female, maybe that makes me know that there's a greater probability that you have a graduate degree or something like that. That would mean that these are not independent. Our probabilities changed by us knowing information about one variable about the probabilities of our second variable. So in this case, our alternative hypothesis would be, no, they're not independent. They're dependent on one another. There's some dependency between those variables. That would be very, very good information for us to know to make predictions. Finally, in section 11.4, we'll look at a test for homogeneity, and we can kind of see this in the same data as before with our men and women and our education status. What we might want to ask are, do these 2 samples that we've taken, one sample of men and one sample of women, do they follow the same distribution? So in this case with 11.4, we're really considering these 2 separate samples, and we're asking the question, do these 2 samples follow the same distribution as one another? Notice the important thing here is we don't have to have a null hypothesized distribution like we have in the dice rolling example. Here, the null hypothesis tells us how we expected the dice to be rolled, an equally likely number of rolls of each of the values. In the test for homogeneity, we're not saying there's some proposed known thing that we're going to match. We're just asking, are these 2 things coming from the same distribution or not? Do they seem to be distributed the same? So let's go ahead and look at our first goodness of fit test. Today we're going to do 2 goodness of fit tests. That's our section 11.2 stuff. In tomorrow's video, we'll look at 11.3 and 11.4, our tests for independence and our tests for homogeneity. So to start off, we're just going to do exactly this dice rolling example that I started with right here. Suppose we have a 6-sided die, and we're unsure if it's a fair die. We're thinking, we're suspicious that there's maybe a chance that this is actually a loaded die and it's going to roll some number more likely than other numbers. So we're going to roll this die 60 times, and we're going to look at our observations and see if this determines for us that this is truly a fair die or not. Right? So let's determine at this alpha equals 0.05 level of significance if this represents a fair die or not. So right away, I want to be a little bit careful with my hypotheses here. I did already state what the null and alternative hypothesis should be for this experiment here, but I do think that we should state it in a couple alternative different ways here. So I think the simplest way I can say this is the die is fair. But this doesn't really tell me anything mathematically speaking for myself. So I'm thinking that a different way that I could say this would be to describe the probabilities that I expect for each of the outcomes here. I think that the probability of our of rolling a 1 should be equal to the probability of rolling a 2, should be equal to the probability of rolling a 3, should be equal to the probability of rolling a 4, should be equal to the probability of rolling a 5, should be equal to the probability of rolling a 6, and those should all be equal to 1/6. This is a much more mathematical statement right here, saying I think that all of my outcomes probabilities are equal, and I know what I think they're equal to, a 1/6 chance for each of them. Another way to say this, which is sort of halfway in between, this is our wordy mathematical way, would be to say um, the outcomes from rolls of a die are uniformly distributed right? The uniform distribution, that's us referencing something mathematical right there, right? The uniform distribution is a defined distribution where we know that there is an equally likely outcome of all possible outcomes. Each outcome is equally likely. So how do we then form an alternative hypothesis? Well, we could either say the die is not fair, or we might say, referencing our second null hypothesis, maybe saying something like not all probabilities are equal. 1/6. And that's just a k right there. I'm just saying any of my x equals some number statements, not all of them are going to be equal to 1/6. That would be a way to say that. Or we could just say the rolls of this die are not uniformly distributed. Right, so we've kind of got some options with these right here. I kind of think I prefer the slightly more technical one. I think our first choice on each of these is the lamest one right here, but it's definitely true. Remember, our null hypothesis is always our statement of no change or no difference. Our baseline assumption every time you pick up a die is we always sort of assume that the die is fair unless we kind of have good reason to believe that it's not right here. So the standard scenario for any given die is that it is fair. So that's our null hypothesis. If we see extreme evidence suggesting that it's incredibly unlikely to see rolls like this if it were fair, then that will lead us to reject the null hypothesis in favor of the alternative hypothesis. The die is not fair. There must be some probability that is not equal to 1/6. They're not uniformly distributed here. So one of our big things that we care about here with our test statistic is to compute a test statistic. We want to get a measure of how unusual is the sample that we've collected here. So let me say here, in general, so what I'm going to do is I'm going to make a little table here to help myself out with this guy. Right? And by the way, Excel is going to be incredibly useful for us here today. We'll do both these guys both by hand in Excel. So what I'm kind of thinking for myself here is I'm going to make a little table. I'm going to start my table like this. It rolls the die. Get out of here, p-value. Now, I'm going to go grab my observed counts. How many counts did we observe in our sample? All right, that's what I'm saying when I say observed. What did we observe in our sample? 7, 6, 11, 10, 8, 18. 7, 6, 11, 10, 8, 18. Those were the observed rolls that we saw. Now, in this case, we knew to expect that there was going to be a uniform distribution across each of these guys here. Since we rolled 60 times and we think that there's a 1/6 chance for each roll, all of these expected counts should be 1/6 of 60, which is 10. So I expected to get 10 of each of those outcomes if I rolled the die 60 times, right? Now, what we know is that it would honestly be pretty weird if we rolled the die 60 times and got exactly 10 of each different outcome, right? We always expect some variation in every single sample that we draw. So some variation is normal. If this variation gets too extreme, that's what's going to push us over the edge and say, you know what? No, I think we're rejecting the null hypothesis here, stuff like that, right? So in general, we reference each of these as our O's and our E's. You'll see lots and lots of O's and E's in this chapter out here for our observed values and our expected values. In general, we are going to compute our test statistic, our chi-square test statistic, as the sum of the observed values minus the expected values squared divided by the expected values here. All right, so what we want to do then is we want to go ahead and compute this value here. So our test statistic, our measure of how far off or sort of where we are located on that x-axis out there of our chi-squared graphical distribution is going to be measured by adding up, this is a sum, this calculation. Our observed minus expected, how far off was what we observed from what we expected? Part of the reason that we're squaring here is because we don't want, for example, I'm trying to see, did I get anything like this here? Not quite. So notice that if this 11, for example, were a 12, then that would have mean we saw 2 more than we expected. We don't want that to cancel out with 8 compared to 10 being 2 less than we expected. We don't want those to say there was no deviation with a positive 2 and a negative 2 to cancel. We want to accrue all of our deviation here. So squaring is one good way to handle that, where it makes sure that we don't let 2 above and 2 below represents no deviation. We want to accumulate all the deviation associated with them. And what we also want to say here is our observed minus our expected, being off by what you expected by 2 is a very big deal if you expected to get an outcome of like 2. If you got 4, then that's twice as much as you expected. On the other hand, if you're off by 2 and you expected 100, well, 102 is not that far off from 100, right? So when we divide by the expected right here, this is doing a sense of standardizing. This is saying proportionally how far off were we from what we expected. So what I want to compute then is I want to compute this for each of our different rows here, and then we will sum them. We will add them all up. So I'm going to do here O minus E squared and O minus E squared over E. I'm going to sort of build my terms part by part by part here. All right. So what's my observed minus my expected? 7 minus 10. That one was 3 below what we expected. We got 4 fewer 2's than we expected. We got 1 more 3 than we expected. We got exactly as many 4's as we expected. We got 2 fewer 8's than we expected. And we got 8 more 6's than we expected. That's sort of our extreme one right there, that we're sort of suspicious that's the thing that makes me feel like this is suspicious, right? So to proceed on with our math, I know I'm trying to construct this sum of all these terms, so I'm trying to still build the term. Let's go ahead and square all these now. 9, 16, 1, 0, 4, and 64, right? So what I'm noticing is that since we're about to do a sum, what I'm kind of noticing is that this part of the sum is going to be the biggest contribution. I don't care what we're dividing by. Well, we're dividing by the same number for expected in all these cases. So notice that our expected is 10. for all of these guys because this was a uniform distribution. So 9 divided by 10 is just 0.9. 16 divided by 10, 1.6. This will be a 0.1, still a 0, 0.4, and a 6.4. All right, so notice here, we can now add all of these guys up, and we will have summed the difference between the observed and the expected squared, all divided by the expected. And this will be our test statistic associated with this sample that we've drawn here. So going to my calculator, I've got a 0.9 plus 1.6 plus 0.1 plus 0.4 plus 6.4, and I'm getting 9.4 in total here. So what we have done is we have computed our test statistic associated with this sample that we've drawn. We expected there to be a uniform distribution across these 60 roles, so we got our expected counts from that. We had our observed counts, and now we've done a comparison of our observed counts relative to the expected counts, and we have come up with some form of computation that's associated with this here, right? Now, where we know we're going with this is the same place we kind of always go with this in our hypothesis testing. Since we have computed a test statistic, our next mission is to compute the p-value that is associated with this test statistic. Let me say, it is still the case that the p-value represents the probability that if we were to perform this experiment again, that we'd see results at least as extreme as the result you've already seen. Therefore, we still need to compute the area under a chi-square distribution curve and to know which chi-square distribution, we need to know the number of degrees of freedom. For this test, number of degrees of freedom is 1 fewer than the number of possible outcomes. All right, so let's kind of see what I just wrote right here, split up across my page. It's still the case. This is our standard definition of p-value. P-value represents the probability that if we did this whole experiment a second time, we'd see results at least as extreme as what we've already seen. So we still want to compute this area underneath a probability curve in the more extreme direction. But what we've seen is that there's lots of different chi-square distributions depending on how many degrees of freedom we have. So what we need to know is how many degrees of freedom do we have? When we're performing our test for goodness of fit, it will always be the case that the number of degrees of freedom is 1 fewer than the number of possible outcomes. In this case, there are 6 possible outcomes associated with rolling a die. Therefore, we will have 5 degrees of freedom, right? So it's number of outcomes minus 1. Let me say that here. And that's only for this one. We'll get a different way to compute number of degrees of freedom coming up here in a minute. So let me kind of show you just real quickly what this looks like. I kind of want to actually come back to these statements that we were making about our graph here a minute ago. I'm going to pop over into our browser real quick right here, and let me show you guys something I kind of found that was pretty cool here. Oops, that's not how I want to drag that. This graph right here is going to show us a bunch of different chi-square distributions. All right, so this is just a graph. I just Googled chi-square distribution Desmos, and it turns out that there's some nerd that put a whole bunch of work into making Desmos be able to understand a chi-square distribution and all of its various graphs. The really important thing that I want you to keep your eyes on here is that I'm going to change the number of degrees of freedom. Right now, we currently are at 4 degrees of freedom. I'm going to reduce this down to our one scenario. So notice here, when we have only 1 degree of freedom, when there are only 2 possible outcomes, for example, this would be like if we're talking about our probabilities associated with flipping a coin and determining if it's fair. Since there are 2 outcomes when flipping a coin, heads and tails, that we would have 1 degree of freedom, and our graph will look like this, which is kind of crazy because this looks wildly different from all the graphs that we've seen this semester. Notice that just going to 2 degrees of freedom, okay, it's still sort of got that same shape of only decreasing. By the time we get to 3 degrees of freedom, we're starting to get a shape that kind of has a little bit of an up and down like most of the distributions we've seen this semester. However, I'm very hopeful that all of you feel very confident in saying this is not looking anything like a normal distribution because normal distributions are symmetric and bell-shaped. But notice that as we increase our number, so ignore that red right now, by the way, just focus on the blue line right here. Notice that as we increase our number of degrees of freedom, what happens to the shape of this distribution? Well, if you ever suggested that this thing looks even remotely normal, I'm just going to fail you this semester. Normal distributions are symmetric, dang it. But I do think it is a very interesting observation that as we let the number of degrees of freedom get bigger and bigger, this is looking closer and closer to being normal. And in fact, if we were to extend this thing like way out here, I'm gonna go extra far on this guy right here, and then I'm gonna let this guy get a lot bigger as well. Then now I'm going to slide this thing out here and we're watching. So it's getting really low and flat right there. It's getting a little bit harder to judge, but maybe I could just make this more like something like that. Make this, there we go, so that we can actually see it. Notice that now that we're out at like 100 degrees of freedom, I can kind of tell that this right tail is still a little bit longer than the left tail, but this is looking pretty dang close to being normal here. And notice that when we're at 100 degrees of freedom, the maximum value occurs when our x value is at 98. So what actually ends up happening here is as our number of degrees of freedom tends off towards infinity, this actually does become a normal distribution where the average is going to end up being equal to the number of degrees of freedom. But that only happens when we get a huge number of degrees of freedom that are out there, right? We are looking at a scenario where we have only 5 degrees of freedom. So we're working with this distribution right here, not even remotely normally distributed, right? So now that's not really an issue for us here. Uh-oh, now I really did it. Let me change my, let's see here. Or actually, I think I can just do this. Yeah, there we go. So our scenario is this right here. We're looking at this guy. We've got 5 degrees of freedom because there were 6 possible outcomes. What we just observed was, what did we get? Actually, we got something really close to this guy right here. We got 9.4. Wow, that's actually surprisingly really close. Oh, bam, right there. This is exactly our graph associated with our current situation right here. What we're interested in knowing is exactly how much area is this in red. And by the way, Desmos is just really struggling to shade. Watch this. See how this is like jumping around all the time. And if I zoom in and out, it like changes shading. It's just struggling to compute that. The point here is we observed a value, and notice here, this is sliding us left and right. We observed a test statistic of 9.4. Oh my gosh, just stop right there. Of 9.4 with 5 associated degrees of freedom. What we want to know is what is the probability that we would see something at least as extreme as this if we were to perform this experiment again. So what we want to know is how much area is underneath this tail out to the right. This will be our p-value. All right, so let's go over into Excel now and make that computation here. So I think I want to like draw this associated picture here. Or actually, here's what I'm going to do for the notes. Is I'm going to take this guy right here, and I'm going to copy it so that we can see it. And then I am also going to take a snip of it. And let's go ahead and copy that. And I'm going to throw it in right here. All right. Whoa. So in this case right here, we've got our, this is our chi, that's concerning. Am I not drawing this? Don't move, picture, just stay there. Oh, really? Okay. This is our chi-square distribution with 5 degrees of freedom. This is our test statistic. Chi-square equals 9.4. This area is our p-value. Remember that the area underneath the probability curve is the probability of seeing that event. In this case, it's the probability of seeing an event that is at least having a chi-squared test statistic of 9.4 or more. That is our definition in this case of at least as extreme. So to compute this probability, we're going to go, and I'm going to go into Excel for this guy. And let's go ahead and bring up our Excel stuff right here. And I'm just going to do this one. I'm just going to lay it over the top for this week right here. Going into Excel, we know that we have 5 degrees of freedom. We saw a test statistic of 9.4. And so over here in Excel, I'm going to do equals. Just like we've seen norm.dist and t.dist, here we're going to have chi-square.dist, CHISQ.dist. What does it want from us? It wants our test statistic. It is unfortunately still calling it x, but at least x looks like that Greek chi squared right there. So our chi-square test statistic is our 9.4. Our number of degrees of freedom is the next piece of information that it wants. That's 5 because there were 6 possible outcomes. Cumulative is always going to be true. And real quickly, what's the one thing I'm sort of forgetting here? By default, all of our probability calculators are always going to give us areas to the left. We are always going to be interested in the chi-square distribution in areas to the right, and so I need to go ahead and throw in my 1 minus in front of this guy to make sure I'm computing a right-tailed area. It is just the default of calculators, just for consistency's sake, that it's always going to compute area to the left of a value. For the chi-squared distribution, we're pretty much always going to be interested in right-tailed stuff, so that 1 minus is important right there. Here I'm seeing 0.094134. Oops. 1 minus this equals, and I'm getting 0.094134. That's our p-value there. So notice that what this is saying to me is that this says if we were to perform this experiment again, there is about a 9% chance that we would see a result at least as extreme as this if we perform this experiment a second time. Oops, sorry, let me get this off the screen here. Nope. All right. So we have now computed our p-value here, and I'm going to write out our interpretation of this p-value. These things matter here. All right, so this says we did this whole dang experiment again. There's a 9.4% chance, right? There's my 9.4% chance. And I'm going to update this. This is just a coincidence that these numbers came out to be so closely related. That 9.4 and this 9.4 is a total coincidence. I'm even going to write that. Right, so if we were to roll this die again, there's about a 9.4134% chance of seeing rolls that are at least as far off from a uniform distribution as the rolls that we saw in our experiment. Finally, if we're going to compare and conclude, we want to notice here that our p-value, let's just say here, since our p-value is greater, that's our important word, we're going to go ahead and fail to reject here. So I would say that the alpha equals 0.05 level of significance. Our data are not significant. They did not represent a significant departure from what we were expecting. Significant, the p-value of 0.094134. We fail to reject the null hypothesis. And conclude we do not have sufficient evidence to show that this is not a fair die. We wanted to show that this wasn't a fair die, and the evidence that we collected just was not extreme enough to show that. And so we failed to reject the null hypothesis there. So what I want to do real quick here is I want to show you guys how we can set this up to kind of like be handled for us slightly nicer in Excel, so that we can kind of play around with this a little bit right here, because this seems kind of crazy to me. That whole 18 sixes seems a little bit wild to me. So I kind of want to show you guys that building this table in Excel is pretty dang easy, and it's a very helpful way for you to be able to kind of play around with some of these numbers. So I'm going to bring Excel back up on the top here. And let's kind of build basically this table right here. So I'm going to leave this as the top visible part right here. And let's see if we can do this in Excel here. I'm going to stretch this up for us a little bit. All right, I'm going to get rid of this. We'll recompute our p-value here. So I'm going to make some, so we've already got our roles. That's actually our index columns 1, 2, 3, 4, 5, 6 on the left. Let's get our observed, and I'm just going to call it O. Let's get our expected. Let's get O minus E. Let's get O minus E squared. And let's get O minus E squared divided by E as all of our columns that we're interested in here. And what we can now do is we can just use Excel's built-in features to help us out with these things here. So by the way, I'm also going to I center these, make it a little nicer. Wait, it didn't center? Center. There we go. So observed, what do we observe? We saw 7, 6, 11, 10, 8, 18. Our expected, in this case, our expected, remember, was the 1/6 of 60. We did the calculation for ourselves that it was 10. In our next example, we'll have not a uniform distribution, and so we're going to want to be a little bit more careful with that one. O minus E, I can now just subtract the first column from the second column. So here I'm going to say is equal to, well, in this case, it would be what's in cell A2 for me minus what's in cell B2 for me. So I'm doing A2 minus B2 here to get what's in cell A2 minus what's in cell B2. Equal sign in front because we're doing a computation. I'll hit enter, and that'll show us that same we're off by, we're 3 below what we expected. Now I can click on this cell, and that'll give me a little square in the corner. And again, watch as my cursor changes to being that plus sign instead of like the empty cross sign. It's a plus sign right there. That's going to allow me to drag this out, and I'm going to get that same computation done across all of these rows right here for me. Again, I can just set up the computation for the first cell here, and we'll drag it out for the column. Now I just want to square what's ever in the C column. All right, so this should be equal to C2, and I'm going to square it. And that gives me 9. I feel good about that computation, so I'll click on it, and let's drag it out. And there's the same values that we expected to see. Finally, I'm going to divide by the expected value here. Notice that all of these expected values that we're dividing by is exactly the B column for us here. So here I'll do, it's that the O minus E squared stuff, that's our D column. And we're dividing it by our B column, dividing it by the expected value right there. And that's going to give me the decimals that we saw. and I can drag that guy out. And again, we're seeing all the same parts right here. So this is all pretty nice for us here. So now I'm going to say this is our uh, chi-square test statistic. And I'm just writing that out in words. And I will say this is now equal to the sum of that stuff in the E column right there. So E2 through E7. I want to add those guys up, and that's going to get me my chi-squared test statistic of 9.4, right? So this is really nicely organized in a table in Excel. Excel's doing all the hard work for me. I've just got to do the organizational work here. My degrees of freedom, that we have by hand computed very easily to be 5 since there were 6 outcomes. And then I can compute my p-value that's going to be associated with this. I'll put this guy right here. My p-value then finally would be my equal to chi-square dot dist. And I can just directly give it E9. That's my chi-square test statistic. I can directly give it E10. That's my degrees of freedom. And true. And I want to remember, I got to stick my 1 minus in here. And that's going to give me exactly what we'd previously seen right there. All right, so let me stretch this out a little bit, and I want to show you why I like doing this in Excel the way that we're doing this right now. The reason why it's nice to do this in Excel is because now I can make alterations without having for me to really worry about doing all the computation again, right? Now I can just by hand change some values over here, and Excel will automatically update what's going on in all of those cells elsewhere, right? So what I can do now is I can say to myself, man, 18 instead of 10 wasn't really extreme enough. Let's see what happens if instead of 18 and 8, we take one of our rolls of a 5 and we give it to one of our rolls of a 6, right? So I'm going to make this a 7 here, and I'm going to make this a 19. And holy cow, look at what that did to our p-value. Our p-value is actually now below that alpha threshold of 0.05. It looks like we were really dang close to seeing something that was extreme enough to represent a departure right there, right? Now, this was us just moving around one roll, right? Originally, this was 8 and 18, right? There we are, back to our original p-value. What happens if we swap some rolls elsewhere, right? This guy, 11, this was one more than we expected. Maybe we give one of these rolls to the 2s right here, right? There were 6 2s, there was 11 3s. I know we're off by 1 from our row number right there because we used row number 1 to be our header right there. So what happens if I just take my 1 extra roll of 3 and I actually give it to the 2s right there? So this will be a 7 and this will be a 10. Remember, our p-value right now is 0.094. That actually made us more, that actually brought our p-value up. Notice that we're actually closer to a uniform distribution now. This used to be 6 off, or sorry, this used to be 4 off, now it's only 3 off. This used to be 1 off, now it's 0 off. We actually brought ourselves closer to being a uniform distribution, and so therefore the probability of seeing things like this happen with the expectation that we're uniform got larger out there, right? So I do like this idea of play around with this in Excel. But maybe we notice, maybe we ask this other question. I want to do this one more time right here. The first time that we changed things, we changed these two and we made it more extreme, right? We took one of these 8 observations away. It was already 2 below what we expected. We made it 3 below what we expected. This was already 8 above what we expected. We made it 9 above what we expected, right? So we made that more extreme. Let's do one more of these more extreme ones right here. For example, in this case right here, I have 6 observations of a 2. Let's bring it down to only 5 observations of a 2. And let's give that extra observation to the 3s. It had 1 more. Let's make it 2 more. So I'm going to make this 5 and 12. Notice that this did bring our p-value down, but not as extremely as it did when we played around with these 2 values. The reason is because our differences, how far off we are from what we expected, is going to get squared. Therefore, large differences from what we expect, like we saw in the 18, are going to make a way bigger contribution to our overall test statistic. This guy that's off by 5, we expected 10 of them and we only got 5 of them. That's pretty far off. But that contribution that it's making to our test statistic is less than half as much of a contribution as being made by being 8 above, right? Being 5 below is less than half as much of a contribution to our deviation as being 8 above was right there, right? So the point here is having everything being off by a little is not going to give us a large test statistic. Having small things be off by a lot is more likely to give us these large test statistics out there because of the fact that we're squaring how much error we had from our expectation that was out there. So let me just kind of fix these numbers so that this isn't wrong right here. There we go. That was exactly the problem that we had right there. And this is good. Now I've got a table that's kind of handling all this calculation for me, and I can play around and see how close were we to rejecting the null hypothesis here. And again, what I could see is I think in pretty much any situation that I would take away one observation here and give it to this count of 18 sixes, I think that would put us over the edge. All right, I promise. Last alteration here. I'm noticing that this is the only one that's also above its expectation right here. So maybe we take one away from this. Let's see if it doesn't have as big of an influence. Notice if I take one observation away from 11 and give it to 18 here, that's actually bringing this more in alignment with what we expected because now it'll be exactly 10. But this is going to get less matching with what we expected. This will become a 19. So what happens if we do this? A 10 and a 19. All right, that still did bring us closer, but notice we're still not over our rejection threshold here. So just by making this a 19 doesn't in all cases cause this to be now so extreme that we reject, because notice that the 4s and the 5s are really, really closely matching with what we expected right there. All right, so now I'll go back and I'll leave this. Oh, wait, this, oh, that was, yeah, okay, that's my 11. And that's my 18, right? So again, I think a really good thing to look at out here is how much contribution are we getting from each of the cells in our table of observed, our observations that are out there. Again, I'm noticing that the number of 4s that we rolled perfectly matched the expected number of 4s, so it provided no contribution to our p-value. 18 was a lot more than what we expected, almost twice as much, and so it contributed a huge amount of our test statistic. Notice that about more than 2/3 of the entire value of our test statistic just came from 1 out of the 6 contributions from it right there, right? So this was really our heavy hitter that helped drag that chi-squared test statistic way far out, which made us have a pretty small p-value, but our p-value wasn't small enough to get underneath our alpha value to cause us to reject. So even this scenario right here, this set of observed rolls of a die, even though we're seeing 18 sixes, this is still not an extreme enough outcome for me to be convinced that this is a loaded die right here, is basically what we've concluded. Right? So let's go ahead and take a look at a second example. And what I want to identify before I get away from Excel here is that the major thing that's going to change in our next example is that here we expected a uniform distribution, meaning we knew that there was an equally likely outcome of all possible outcomes under the null hypothesis. In our second one here, we're going to change this to be a scenario where we don't see the same likelihood of all possible outcomes, and therefore we'll need to be a little bit more careful with our expected column here. So let me kind of bring up Word again here. There we go. And let's go ahead and take a look at our second example here today. So example 2. Suppose that according to the state of California, the state of California wants to track things like how do people get to college campuses, because the state needs to know how much they should be like funding, schools to help their students get transported to and from campus, stuff like that. So suppose that according to the state of California, they report this distribution statewide of how people get to school. 25% just live on campus, 26% walk or bike to campus, 13% take public transportation, and 34% drive to campus. And let me do a real quick sanity check right here. 25 plus 26 plus 13 plus 34. Oh my gosh, that's hilarious. Is not 100. I did my math. I'm glad I did the sanity check. See, that's why we do those things, people. There we go. I add them all up and I only got 98, which is a little bit embarrassing right there. So I'm just going to artificially plop an additional 2% into the drive to campus scenario here. So what the CR administration might then say is, well, do our students match the statewide proportions out there? Because what I'm kind of thinking is this, and especially in states like California, the state is going to look at what's happening on average throughout the state, and then it is going to fund all the individual institutions in the state based on that statewide average. If CR can determine and statistically prove that their students do not get to campus the same way as happens across the statewide level, that might be justification for the state to request additional from the school to request additional funds from the state to help support things like having buses get people to campus and stuff like that. So our question might be, do CR students get to school following the same distribution of transportation modalities as people across the state in general? So what CR is going to do is they're going to take a random sample. It looks like here is 84 students. I better now double check myself again. 6 plus 4 plus 28 plus 46. Yes, they sampled 84 students, so 84 CR students were sampled. They reported 6 of them lived on campus, 4 walked or biked to campus. I'm assuming those were bikers. 28 take public transportation, and 46 drove or got a ride in a car to campus. Let's go ahead and determine at the alpha equal 0.05 level of significance if the distribution of campus transportation modalities for full-time CR students match that statewide distribution. All right? So notice here we have a proposed distribution that we're following. It's not a uniform distribution. It's not equally likely that you're going to bike to campus as it is that you're going to drive to campus, right? We have a different probability of each different outcome right there. Okay. So what we need to do is we need to be a little bit more careful. Notice in our previous example, we computed not the expected proportion of results. We had to compute the expected count that we expected to see. Since there were 60 rolls of a die, we used that 60 to help inform us that there should have been 10 ones, 10 twos, 10 threes, blah, blah, blah. Same thing down here. Rather than saying 25% of students live on campus, we're going to need to take 25% of 84 and determine how many did we expect to see in our sample that we took right here. All right. So let's first talk our hypotheses, and then when we compute our test statistic, we're going to want to go back and play with those observeds and expecteds a little bit right there. So our hypothesis here, our null hypothesis, I'm going to type this one out. I'm going to say our H sub 0, our null hypothesis is going to say, and I'm going to phrase this a couple different ways. CR students, campus, CR, I should be appropriate here, full-time students, transportation, modalities, have a distribution that matches the state average. So our null hypothesis says, this is our statement of no change. We are no different than the state as a whole. There is no change between, oh my gosh, just indent however much you want. Okay. Students, there we go. Another way to say this would to literally just be to state the probability distribution. So I might say my alternate, I shouldn't say that. Another way I could form a null hypothesis here would be to say, CR full-time student transportation modalities follow the distribution. And I'm just going to make a little table of the distribution. And it looks like we have on campus, walk or bike, public trans, and drive. These are our 4 categories. And it was proposed to us 25, 26, 13, 36. Right? This is our proposed distribution of outcomes right there, right? They follow this distribution. This is our probabilities of them using that certain modality to get to campus, right? So these might be our 2 good ways for us to say our null hypothesis. Our alternative hypothesis then would be to say just CR full-time students, distribution of transportation modalities do not follow the statewide distribution. Right? So either we follow it or we don't. It's a yes or no question right here. We want to see, does the sample that we took, we know the sample that we took is going to be deviating a little bit from this. We want to know if that deviation is just due to sample variability or due to a true difference in how CR students get to school relative to the people statewide. So let's go ahead and compute this test statistic here, but I want to be a little bit more careful about how we compute these guys here. Again, we'll do this. I kind of maybe think that we should just do this guy in Excel. I think this is actually going to be way easier for us here. So I think I'm going to set this guy up like this. Here's what I think I'm going to do. I want to insert an extra one right there so that all this stuff matches. And so for this problem here, let's kind of go back up and see what we saw right here. So I'm going to bring Excel back into the picture here. And let's go ahead and fill this stuff out according to what we kind of see on the page right here. So maybe I can shrink us down a little bit for a minute. All right. So what was our modality in each case? We were on campus. Stretch this out a little bit. Walk, bike, public transportation, or drive. Those were our four ways of getting to campus. All right. What we wanted to know was how many did we observe. So I'm going to call that O. We observed 6 that live on campus, 4 that walked or biked, 28 that took public transportation, and 46 that drove. What we want to know is what is our expected as a percent, and then we'll get our expected as counts, which is really what we need. I need to know the count of the expected observations out there. So my expected percents were this 0.25, 0.26, 0.13, and 0.36. So notice what's going on here, and maybe I'll do this sample size, and our sample size in this case was 84, right? So what I'm thinking to myself is if I expected 25% of students to be on campus, right? On campus, our expected percent was 25% according to the state of California. If I expected 25% of CR students to be living on campus out of 84%, then I can do equals 84 times the expected percent. That's C16 for me right here, right? That will tell me I expected to see 21 CR students living on campus if we did in fact follow the statewide distribution. We only saw 6 that lived on campus instead. Pretty big deviation right there. Again, I can click and drag this guy out. This should keep my 84 times the appropriate thing, right? So this is, if you're looking up top up here, you can see that all this is 84 times C17. So it's saying we expected, and now notice, it's certainly the case that I can't have 21.84 people walk or bike to campus, but this is still according to our percentages what we would expect to see. If we did this experiment many times, we'd expect to see on average 21.84 people walking or biking to campus across the state out there, right? We expected 36% to drive to campus. 36% of 84 is 30.24. So all this was a little multiplication, right? 36% of 84, I multiplied those two numbers, and that gave me an expected count of 30.24, right? So let's just kind of notice that what we're really directly comparing is these two columns. The expected percentages were given to us, but we needed the expected counts to actually make our computations happen here, all right? So we're saying we saw 6 people lived on campus when we expected 21. Big difference. We saw 4 people walk or bike to campus when we expected 21.84. Big difference. We saw 28 students use public transportation. We expected only about 11. Big difference. We saw 46 students drive to campus. We expected only about 30 in our sample. Pretty big difference. So I'm seeing here, this seems to pretty wildly differ from the null hypothesized distribution, right? This does not seem to be reflective of this right here, all right? So when we compare now our observed counts minus our expected counts, this will help us compute our chi-squared test statistic here, all right? So let's go ahead and make this a little bit bigger so we can see a little bit more of the stuff right here. And what I want to do is I want to build this table kind of the same way as we built our previous. I'm going to make this quite a bit bigger right here. So in our previous example, we had found, let me bold this one just for the sake of it here. I might as well do this. All right, I kind of want to build the same table. Notice that we have one additional column here because we are given the percentages of expected. We need to use that to get our counts of expected. This E and this E counts are the same column. It's the counts that we expected to see in our sample if our sample truly did follow the null hypothesis here. So we now need to go ahead and compute these three columns right here. Might as well just copy and paste those column headers over. Give me that crap. And here we are. Let's go ahead and do this here. So observed minus expected. My first observed value is right there. It's B16. My first expected count is right there. It's D16. So I'm going to go ahead and do equals B16 minus D16. And that'll find my observed minus my expected counts. That says that we saw 15 fewer people living on campus than we expected under the null hypothesis. And I'll drag this out to perform that same computation. Now we want to square all these guys, so that's going to be equals E16. E16 is the slot right next to me. Let's go ahead and square it. I do know that that is 15 squared, and it got rid of the negative as we should expect. And there's all of my observed minus expecteds squared. Finally, we want to divide this by the expected, and again, it's the counts that we're looking at. Don't do weird things to me. It's not the expected percentages. We never really use this column except to just create the actual E column that we actually want right there. So let's now go ahead and do this equals F16. I want to take my difference squared and divide it by what I actually expected to see. That's my D16. So that's what I'm dividing by is D16. And this is telling me how much contribution I'm getting to my chi-squared test statistic. All right. So we can see here we're getting a pretty reasonable contribution to the chi-squared test statistic in all cases right here. All of these had some pretty decent deviation from their expectation. And so now we can go ahead and add these guys up. This is our chi-square test statistic. And that's just equal to the sum of this column. And that is G16 up through G19. And that's going to tell me my test statistic in this case is a chi-squared value of about 60.2. How many degrees of freedom do we have here? Well, remember that in this case, our number of degrees of freedom is always our number of possible outcomes minus 1. Here there were 4 possible outcomes, so we have 3 degrees of freedom. Before we move on then, I want to, let me kind of throw some of this stuff. By the way, notice that, sorry. Let me come back into Word and throw some stuff into Word here. And then we'll come back to Excel to get our p-value here. As we computed in Excel, we get a test statistic of chi-squared. And notice, by the way, chi is exactly that, like kind of curvy x right there, of chi-squared test statistic being equal to, and what did we just get? We just got 60.215 with degrees of freedom equal to 3. Since there were 4 possible outcomes. What I would like to do is I would like to come back to Desmos real quick here and kind of throw the same information in here so that we can get our graph again. And then this is just to help visualize this guy. Notice that our 3 degrees of freedom situation is this very, very, very skewed graph. This is heavily right skewed. The tail is to the right. And notice where we're at on this graph. Where we're at on this graph is we're literally out here at 60, asking how much area is to the right. And you should be seeing that that area is essentially 0, right? This is a huge test statistic. We're getting a test statistic of about 60. We're asking how much area is underneath the graph to the right of 60 out there. Our answer should be essentially 0, and I can tell that just by looking at a graph. But again, notice that just seeing a chi-squared test statistic of 60, that's not enough information. The degrees of freedom are required. Notice, by the way, if I were to drag this number of degrees of freedom out here, if I kept on going, if I made this something more out there, then notice out here, for example, if we had 60 degrees of freedom, then there's a huge amount of area underneath our curve to the right of 60. And therefore, we're going to get a very large p-value instead of a p-value that's almost zero, like we'll get in our case here. So notice that just knowing the chi-squared test statistic isn't enough. We need to know how many degrees of freedom it's associated with to get an idea of the probabilities associated with it. That is different than in the standard normal or the normal distribution, right? If I said to you, I am 2 standard deviations above normal, that's all I need to tell you for me to be able to compute relevant probabilities because there's not multiple different normal distributions. In this case, there are multiple different chi-squared distributions, so just knowing that we have a chi-squared test statistic of 60, it's not enough for me to compute or even estimate my probabilities. In the graph right now, the chi-squared test statistic of 60 would give us a p-value of about 50%. About half the values are to the right and half the values are to the left of 60, or the area. On the other hand, when we come back down to 3, we can see that about 100% of the area is to the left of 60 and about 0% is to the right of 60 out there, right? So this degrees of freedom hugely influences the shape and location of this chi-squared distribution. So while you don't necessarily need to see these graphs out here all the time, I think it's really helpful to just remember that the chi-squared distribution takes on so many different shapes that the number of degrees of freedom does have a huge influence on the probabilities that we end up computing out here. So let me do this real quick. And I want to just do a little bit of zooming out here, but I'm going to drop that down to 3. I'm again going to take my little snip of this guy. Let's come back to Word. Two things I want to copy and paste into Word here. One, I want my graph in here. We'll leave that guy alone. 2, I'm going to also grab a little snippet of Excel here. All right, so let me kind of label some of the items that we see on here. And so a couple things I'm seeing are, oh, come on, let me write on this thing, dang it. Oh my gosh, oh my gosh, oh my gosh. I'm obviously drawing. I'm obviously drawing. We're drawing here, buddy. So this is our, oh my gosh, apparently it's not obvious. Do I want to make this a behind thing? Okay, so it's not possible apparently for me to write on this graph, so I'm just going to stop trying. And I'll just write everything to the side in a slightly worse place. All right, so now we've computed our test statistic right here, right? This is sort of our answer to this part right here. Oh, sure, I'm allowed to draw in this picture all of a sudden. Hey, very cool, Microsoft Word, very cool. So we can now go ahead and compute our p-value. This is where we're going to come back into Excel to get a little p-value computation here. So let me bring that guy back up. Right. So we had that 60.2. I'm going to go ahead and compute our p-value here to be equals 1 minus. I know it's going to be 1 minus. I'm going to look for that right tail, our more extreme situation right here. Chi-square dot dist. What am I putting in? I'm putting in my chi-squared test statistic, which I have in cell G21. I'm putting in my number of degrees of freedom, which I have in G22. Cumulative will always be true. And notice it is telling me 5.29e negative 13. That says move that decimal 13 places to the left right here. That's pretty dang extreme. So we're getting here our p-value equals, and again, what was that? That was a 5.29 e negative 13. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? Our decimal was there after that 13th digit. We moved it 13 places to the left right there. So this is essentially equal to 0. So this says to us, if the null hypothesis really were true, and CR students really did actually follow the same distribution of transportation modalities as the whole state, then there is only a 0.00000000000 0.529% chance that we would draw another sample from CR students and see a distribution like we saw again. Hey, Kiwi Gamer, how's it going? And so this is saying to us, there's basically no chance that CR students are following the distribution according to the state right here. We have a p-value that is way less than our alpha value here. So since we have our p-value is much less than our alpha, we will reject the null. That's sort of my short statement right there. My real conclusion statement is at the alpha equals 0.05 level of significance, our data are significant. They did show a statistically significant difference from what we expected. Our data are significant, I should say, our p-value. And here, I think what I want to say, p-value is approximately 0, is what I think it's most appropriate to say right there. So we reject the null hypothesis and conclude that, let me say this carefully, that the distribution of campus transportation modalities for full-time CR students does not match the statewide distribution. All right. So again, we asked ourselves, does CR's distribution match the statewide distribution? Oh, sorry, I left that blocked, but not too overly blocked right there. It's okay. There's my conclusion right there. Since we have a p-value less than alpha, we will reject the null hypothesis. Our conclusion saying at the alpha equal 0.05 level of significance, that was given to us in the problem, our data are significant. We have a statistically significant difference from what we expected to see with a p-value that's essentially 0. So we reject the null hypothesis and we conclude that the distribution of campus transportation modalities for full-time CR students does not match the statewide distribution. Not is sort of our important word here, saying it wasn't what we were going into this expecting to see out there. So I'd really encourage you guys to think about doing these ones in Excel, even if you're otherwise working not in Excel so far this semester. Notice that building these tables by hand is really not that bad, like we kind of did right here. That was very reasonable for us to do, and it remains generally mostly pretty reasonable to do these tables as well by hand. Some other things to notice is that, for example, these three columns on the right over here, once you get just a little bit comfortable with this math, I think it's very easy for you to kind of skip these two like work showing columns right here and just immediately go to the O minus E squared over E column right there, right? Like you could do that all in one step in your calculator. Just go right to that final row, write down all of your terms, add them up, you got your chi-squared test statistic out there. Again, notice that computing our p-values ultimately still just results in us going and doing one probability computation, which very, very much mimics the ones that we've been doing up until now to actually compute those probabilities. We still have a graph that we can think about to help compare these. And by the way, when you go back to reference my notes, you'll be able to click on this link so that you can produce your own graphs out there that'll help you do your little sliding around out there. We're still finding that our test statistic is a location on the x-axis, and our p-value is the probability is that is equal to the area under the curve in the more extreme direction. In our chi-squared test, it's always going to be that our more extreme direction is the upper direction, so there's always going to be that 1 minus that's associated with it. And we're still looking to make our same comparison. If our p-value, if the probability of our event occurring is less than alpha value, meaning it's more rare than our rareness threshold, then that's going to be too rare for us to continue believing in the null hypothesis, and so we'll reject the null hypothesis in those cases in favor of the alternative hypothesis out there. So again, think about doing this in Excel if you can. All of you have access to Excel with your CR account. You can just type in Microsoft Office College of the Redwoods, and it'll take you directly to the page where you can download it. Google Sheets is available without even having a download. You can make Google Docs that do this stuff. Google Sheets will do this. Lots of free resources to do this in a slightly more cell-based approach. And I'm just suggesting this to you because I think it's the least work you can do. I'm trying to make everybody do the least work possible here. And I think the most easy way for you to manage the calculations associated with this is going to be to let Excel do it for you. I think I'm trying to minimize your efforts here. So I think finding a spreadsheet way to do this is going to be in your favor for these computations that are associated with this. And I do want to say in our next two sections where we're going to get our test for independence and our test for homogeneity, the same thing is going to be true. Setting this stuff up as a table in Excel is going to be beneficial for us to help keep things organized, make sure we don't make small mistakes. As you can see, there's lots of small computations that happened in this stuff here today. We don't want to let that kind of, we don't want to be wrong because we forgot to square one number or something like that. Doing things in Excel prevents you from making small, stupid mistakes like that. So again, I'd highly encourage you to get into a spreadsheet to make these guys happen. So that wraps it up for me today. In tomorrow's video, we're going to look at 11.3 and 11.4, our test for independence and our test for homogeneity. You should expect to see a lot of very similar things. The only difference is that we're going to end up seeing two-way tables instead of a table of just one variable. We kept on collecting one variable's information here today. What roll did we get from the die? What was your modality for getting to campus? That was one variable. In the next two sections, we'll look at comparing two variables like gender and education status, stuff like that. So we'll expect to see tables where there are multiple cells rather than just like one row or just one column of information in there. But other than that, they should all feel relatively similar when we go to do our computations tomorrow. So I'll see you guys in the next video. Have a good one, everybody.